Hi, welcome to Digital Electronic. I'm going to talk more detail about subtopic 5.3 Latch. So Latch is actually is a transfer latch that copy the output D to the Q. So basically, there is a situation where you need to have a, a traffic controller system. For example, you need to stream a data. You have 0110 or something, and suddenly you need to hold it for to pause it for a certain moment before you allow it again. So let's say you assume you are watching a movie, and suddenly you need to pause it for a certain minutes, and then after that you resume again. So that is how, or that is why the latch will come in. So in this particular topic, so you can see how the latch help you. So if you see over here, this is your typical latch, and you have an extra of a setting of this one. So this particular will have two input, which is your D and you enable. So your D is going directly to the first NAND gate, and you are going to have a enable. You're going to have a D bar over here, and D bar is going here. So your let's say so yeah, so your D bar is going here, your D is going here, and your enable is going here. So your enable is over here, your enable is over here. So the output of this situation will go directly to this particular situation. So here the enable will work as a controller for the input over here. So if you see back your situation, so let's say your NAND gate. So if you have a NAND gate, you have a B, Z. So you have 0, 0, 0, 1, 1, 0, and 1, 1. So in your NAND gate, when you have a 0, 0, the output is going to be 1. 0, 1 is also 1. 1, 0 is 1, and 0, 1, 1 is 0. So for example, in this situation, if you see over here, let's say the enable is going to be either 0 or 1 over here. So let's say we take the enable 0 first. So let's say you have a enable 0. So let's say you have over here is a 0. So you're going to have an output of 1. Over here you have a 1, 0. So you're going to have an output 1. Here there is another 0. You're going to have an output 1. But when there is no 0, the output is always 0. So over here, if let's say your enable is 0, so let's say your enable is 0, and over here 0. Anything with 0, you're going to have 1 over here. And anything with D bar, let's say D, anything with 0, you're going to have a 1 according to your non-truth table. So 1, 1 will go in, and after it reach this one, this particular situation will cause you 1, 1. If you see back your non-latch previously, so your situation will have a situation where you have the enable of a whole, a situation of a whole where this is become 1, 1. So and the output is going to be whole. So your situation will be, so when your situation is 1, 1 over here, so your none will cause you to have a whole situation in this particular output. So whenever you have an output of whole, this will hold when the enable is 0, so the Q will be holding position. So let's see how it works for the enable equals to 1. Let's So when your enable is equals to 1, let's say you have a 1 over here, and your enable is let's say you have an enable of 1, uh, the current situation will make you to have a situation where the output of your so if you see over here, the D and 1 is going here, and when you have an output 1 1, let's say this A is changed to uh, an situation, and this will come out with your upside down. This will become a D bar, and this one will become a D, and this particular D bar is going to is a process of a inverted of this one, and this Q is going to be depending on this situation. So it's always going to depend on the situation of a D bar. So as showing as in this particular truth table. So whenever you have an enable of 1, so you have a 0 1, so 0 0 will have a Q of 0, and whenever you have a 1, this will be become 1, repeating again exactly the same value. But when your enable is 0, so this will become a whole. So it don't care about your situation of D, so this always become the previous data. So this is a timing diagram example. So you have a D over here, your enable is 1, so whenever the enable is 1 is going to repeat back the D. So you see over here enable is 1, from here to here enable is 1, so it's going to repeat everything again, such a similar situation. But exactly over here, when the enable is becoming from 1 to 0, here the last bit over here is equals to 1. That's why over here is always 1. Even though here change, here it doesn't change, so it's going to be always 1 until the enable become 0 to become 1 again. So over here it will start to repeat whatever the data over here, so that's why you get the same result over here. So the D-latch has been explained, so let's go for a small example. So first, when you have such a question like this, first make sure you understand where is the D and where is the enable. So after you make it, first step is always to draw the branches. So the timing diagram. So over here, the changes is have always happen at the enable. So this is the part where the changes always happen. So be make sure to draw a line. I'm sorry. So please make sure to draw a line exactly over here, exactly over here, exactly over here, such like this. And then whenever enable is equals to 1, so enable is 1, always repeat back whatever over here to become like this. Whenever enable is to 0, the last bit over here is focusing as 1, so that's why your data will be focusing directly same as this. And this one is because the enable is changed from 0 to 1, so this will repeat everything over here again, and over here is 0, so the enable is changing from 1 to 0, so this will hold this data, so that's why will become a 0 over here. So let's check. So yeah, correct. So you're going to have the similar situation like here. This is 1, 1 1 1. This is 0 0 0. So this is 111 111 and this is 000. So the condition of the usage of the D latch has been explained in this particular work. So once again, you need to understand the active high and active low concept before you go for the flip-flop. So active high, when the output is not, there is no bubbles, and active low is having a bubble. So for example, this one is active low and this one is active high. So the easiest term to understand active high is it will be active when it is in high mode. So that means high mode means one. So when there is a output of is there is an input of one or output of one, it will be activated. Or this is whenever is zero, this will be activated. So please take note of this particular situation. So this is active low input of a knowledge. This is active high of a knowledge. So just take note about the bubbles. So these bubbles are, so there is a possibility where some situation or examination or any kind of test, they didn't mention anything about this. They just say, let's use active high input of SC flip flop, for example. So you need to know that your input is going to be no bubbles. So uh, this is the basic understanding of active high and active low by diagram. So this one is a synchronous and asynchronous. Synchronous situation. When you talk about synchronous and asynchronous, it's always depending on the clock. Clock is the important situation. What is clock? Clock is a situation where you have a timer. For example, a situation of like this. So when you have a situation like this, you're going to have a timer. Why time is so important is this frequency or this particular pulse is will define when to have a situation to change a particular output. So for that, we're going to have a common or non-common clock. That is the timer. So this particular timer have a response. Let's say you're going to have a rice type. So that means at this particular area, you're going to okay, for example, you set in your programming, I want my output, I want my chip to be respond for each two cycle of a time. So let's say this is the first time you need to respond. This one you don't need to respond, and this one the second time you respond, this one you don't need to respond. So you can program your device to work accordingly. Otherwise, that's why we very important, the clock, the function of clock is very important in this particular situation. So if you see over here, uh, it's a synchronous system. When you say about synchronous system, it responds to a change of input at only discrete instant of time determine a clock. So it highly depending on the clock and the output in the step of the clock system. So like I mentioned earlier, I give an example. So synchronous is always depend on the clock system. So otherwise for asynchronous, it's a response a change of input at any distance. So you can see over here, it's at any instant of time. So it doesn't need to wait for the clock. So for example, like I mentioned over here, I give an example. So you have one, no signal over here, no change over here. The second one, yes. Yeah. Let's say suddenly over here I need to change. So if I change, because I say the rule is always to need to change depend on the rise fall. So suddenly I want to change over here. So this particular area, a change in this particular system at this particular time is we call it as asynchronous system. I hope so it always respond immediately to any particular moment. So this particular asynchronous system, you're going to understand. You're going to go through using for flip-flop system. So flip-flop system, we're going to use clock. As I mentioned earlier, latch maybe no, but the flip-flop yes. So they in the flip-flop, especially in the JK flip-flop, there is a part where you need to depend on synchronous system, but there is a part where you don't need, you just need a asynchronous system. So I will mention in detail later. So clock signal, I think I already covered this earlier. So you need to know is a failing rising edge or falling edge. So rising edge, we always put a symbol like this. This is a rising edge. For falling edge, we always put a signal like this. So sometimes you also can represent this situation in as this one. This is also we call it rising, and we call this one as falling. So please take note on this one. So this is a good example. So this one is I think this one is referring to your duty cycle. So duty cycle, your duty cycle equals to TP over T plus TP times 100. So you're going to have then you're going to have the percentage, how many percent. So for example, this one is should be less than 25% duty cycle. This one is explaining in more detail. So this is positive, this is negative, and for the negative transition, so this is falling and this is rising. So you need to understand whether it is positive or negative going. But usually we only focus on the positive going transition rather than negative one. But it can be any situation depending on the your declaration. So, so until here, thank you. So I hope we're going to focus on 5.5, which is SC flip flop after this.